Our last presentation from Martin Holmes. Martin is a Senior Business Development Manager at Rohde & Schwarz. And you're going to talk about contribution and distribution using unmanaged networks and coming of age.
Thank you, Hans.
You're ready? Yes. Here are your tools.
Lovely. Good morning, everybody. I'm aware that I'm between you and lunch, so we'll go through some of this fairly quickly. I was quite inspired by the last presentation. I come from an environment where we did dual link, we did quad link, and now we're talking about 16 sets of 10 gig Ethernet or multiple sets of 100 gig Ethernet. So I think that's absolutely great. Quite inspiring, really. I love the idea of doing things with 16 switchers and stuff like that. We used to work for a company that made switchers, so it was, you can see there's some value in that too. So my colleague, Dr. Marco Loja, is traveling this week, and I'm going to take you through the information this morning. He sends his apologies for being unable to attend today, and I'll do my best in his absence. So satellite and dedicated fiber links, just to go back, I want to just go back to the previous presentation one more time. They're talking about very large bandwidth pipes to do jobs like that. And I'm going to try to tell you about trying to do things in sort of small bandwidth pipes over non-dedicated networks in a very sort of unmanaged Wild Wild West sort of way using the internet. So it's the exact opposite of the presentation that we've just been through. Satellite and fiber links, dedicated links, have served our industry well for years. Currently there's a growing movement to lower cost and use IP contribution and distribution over the internet. So today I'd like to just discuss some of the challenges of that, internet transmission of sort of high bandwidth, low latency streams, and how some new protocols for internet transmission can address some of these challenges. So this is a fairly simplified description of a typical broadcast signal flow. IP and internet technologies are having a major impact on our industry. I guess that's what we're all doing here this week. And while traditional and dedicated fiber links are reliable, they've proven to be reliable over the years, they're also expensive. And because they're dedicated, they require dedicated architectures to use them in the case of a dedicated satellite truck, or perhaps a dedicated connection to a fiber. So that's how they require that stuff to function. But if you ever look at this, graph, these green tick boxes are areas where IP is available today, and I think that as the technologies develop out, these green tick boxes will migrate farther and farther to the left into the acquisition phase, the sort of acquisition and delivery into a content factory phase. So what I'd like to do with the next couple of slides is just talk very quickly about the different applications for internet contribution and distribution, starting from relatively simple point-to-point links, of course, all the way up to cloud integration and cloud instances aggregating content and distributing as required. This, of course, is a simple point-to-point connection, linking one sender, essentially, to one receiver, though, of course, the links are bidirectional. This is a typical multipoint to multipoint connection. Data comes into the location from a number of, from multiple sources, and it can be integrated in that single sort of location, it's a typical, what we used to call a contribution model. It's the way we used to do contribution. In this case, the hub, if you like, the central location, is in Amsterdam, of course. Sorry about that. Okay. So then there's point to multipoint, sort of the distribution model. So the central location can push data out worldwide, and the worldwide locations, spokes, if you want to call them that, can utilize this data. This is typically used for sports, perhaps, or news, something like that. And then there's a multipoint to multipoint application, where in a video data sharing model, multiple facilities can send, multiple facilities can read, and data is shared across any number of multiple facilities. So this is another one that is near and dear to my heart, the delivery of ATSC data streams, ATSC1 data streams from a hub to spoke cities or spoke locations where transmitters are. These can be high tower locations, or as part of an SFN, of course. There's another one of these is sort of interesting today. As part of, we're in the middle of the transmission repack that plenty of people know about. There is a discussion of having a C-band satellite repack, and using this sort of thing, if you moved the primary to KU or KA, and then used an internet path as a secondary or tertiary delivery process, you could save considerable amounts of money on satellite paths and delivery for contribution links. It's we've been able to measure satellite paths for a quality of service arrangement against internet delivery paths, and they're very similar in many respects. And in one case, we had the internet path more reliable than the C-band uplink path due to rain fade, because the internet doesn't suffer from rain fade necessarily, but it does, of course, suffer from backhoe fade, if that's an allowable term. And we know this happens. We even with disparate paths. I was recently at a place in Manhattan, and they had a path that went this way and a path that went this way. Two disparate vendors, two different suppliers, and they both appeared in the same manhole on 57th Street. Even though both the vendors claimed that it didn't. But clearly it did, because when it filled up with water, it all stopped working. So it was a sort of an interesting thing. So, you know, even within the terms of that, we've got to be a bit careful. Right up to sort of cloud servicing, where all the new protocols, these recent protocols, are software defined. And an advanced user case could employ instances in the cloud. So a protocol running in the cloud that allows easy scale of scale up, and allows additional content aggregators to join and to receive data in a very simple, sort of straightforward way. Interesting to note that the public internet, the dirty internet, the wild network, is used as both the receive and the destination transport mechanism. There you go. Oh, sorry. There you go. So we should probably just talk a little bit about protocols and what happens to various protocols when we pass data through the internet. So UDP and TCP are the fundamental underlying protocols of the internet. UDP is a protocol designed for low latency, loss-tolerant conditions, and offers really fairly a limited set of basic functionality. It forwards packets from a transmitter to a receiver. That's pretty much what UDP does. But it does it quickly. It's low latency. And I think that's very useful for real-time delivery of video streams, particularly sports, stuff like that, stuff we're used to. But while UDP is great for delivering live streams, it's inherently unreliable. This is due to a lack of a windowing mechanism. It doesn't react well to congestion. This leads to packet loss in routers thrown away, so on. And these packet loss can create audio dropouts, video errors, blocking artifacts, that sort of stuff. And they can range, of course, from being quite minor to being quite major, as you can see in our picture of a dog there. UDP, no guarantees of delivery, no flow control, no retransmission, but it's fast, so it's useful. And we'll look at this in a little bit more in a moment. So TCP, on the other hand, is 100% reliable. TCP always guarantees packets. They arrive in the correct order and without duplication. But the trade-off, of course, is delay or latency. So this is why it's not really suitable for the delivery of live streams over large internet distances with long round-trip ping times, or with many router hops or internet provider hops between the two. Even quite minor packet loss can cause TCP to freeze or to limit its bandwidth. And we've all seen that sort of thing. So this problem actually also occurs with all TCP-based protocols that use HTTP. And so some of the streaming protocols like HLS, HTTP live streaming, they're also affected by this limitation. And you end up looking like that. Because HLS is based in TCP, of course, then internet streams can be accessed in the same way. It's convenient. They can be accessed in the same way as other web content. It includes being able to get at the content from behind firewalls and that sort of stuff. But in order to make it work in an OTT way, we need to be able to provide the streams at different bit rates, and then we split all of that bit rate into chunks, and then those chunks, they could be MPEG-2 transport, we'll call them MPEG transport streams for the sake of it, each of which is a number of seconds long. This sort of packetization allows the streaming client to choose the quality profile that it needs to use, but with the obvious decreases in acceptable video quality. This is stuff that you've all seen. So what do we do about it? There are some methods of combining these sorts of protocols. These techniques, they're designed to resolve the challenges of transmitting high bandwidth streams over long distances in unmanaged networks. Many of these are based in UDP because it's the simplest form of sort of data extraction. So most of today's internet transmission protocols, they're working in this sort of problem space. They employ ARC techniques. This is automatic repeat request techniques over UDP. So what it means is that the receiver acknowledges the packet that's arrived, and then the transmitter essentially sends another one. There's a more advanced approach, perhaps we could say, the negative acknowledge, the NAC, and that's when it only sends a request when it doesn't receive the packet it thinks it's going to get. So missing packets at the receiver are requested to be sent again by the transmitter. All relatively simple. The approach requires retransmission buffers, of course, to be available at the transmission site. So we have to engineer that into tools to make this work. And only packets that are still in the buffer can be sent again. So we then have to build fairly obviously quite large buffers, which leads to delay and that sort of stuff. So the trick of using the buffers is to make sure that you automatically build them big enough, but not so big that you introduce additional delay. So this is a sort of an interesting one, in as much as we develop more complex codecs, and we rely on them for more and more impingement upon the images that are around it before and after. If you drop a packet of an MPEG-2 transport stream, you drop a packet. If you drop a packet of an HEVC transport stream, you can really damage the resultant image because of the complexity of the codec and the interdependencies of all of the data that's reliant on the frames that came before and the frames that came after, or the blocks that came before and blocks came after. So when we deal with round trip times between servers and between sources, we're often looking at tens of milliseconds. It's sort of a good rule of thumb is you can double the round trip ping time. That gets you close to pretty much what you've got to do. But do bear in mind that the journey of 1,000 miles takes 5 milliseconds at the speed of light. So it does take some time to do what it needs to do. But well-engineered solutions can actually get to this data and make it work in a way that we can use it. So I've spent a long time talking about this stuff. I think the best thing to do is what I'd like to do is show you some pictures. That's I think the best thing for us to do. So this is a look at the effect of bandwidth on a UDP stream. This case, this allows us to, the original is in the top left window, the receiver is in the bottom left window, and up in this top corner here, you can see the packet loss rate expressed as a percentage of packet loss. And even at 1% packet loss, you can sort of see what happens at the receiver. So that's 1% packet loss. So over in the, we'll get to this last window in a moment. But as you start to ramp up the percentage packet loss, it gets progressively worse and worse. And once you get beyond, I mean, you can take this all the way out to 50%. And once you're at 50% packet loss, which is where we'll go, I think, in a moment, you'll be able to see that it's, it's truly broken. But this bottom right-hand side is the result of using one of these streaming protocols, one of these modern streaming protocols that we'll get to at the end, that's able to reconstruct this data using this much packet loss. And just for purposes of completeness, at 65% packet loss, you can see that the process stream starts to break. So this is quite a good test at up to 50% packet loss. You can actually see how broken these things get and what you can do to recover the data from that. And this goes on in a loop. So this is another one. So this is the effect of reducing the available bandwidth to a UDP stream. So this is what UDP does when you limit it to limit its bandwidth and it starts to drop packets. This is an open source bit of software called WAN-M, and you can control all kinds of things with that: packet loss, delay, available bandwidth, that sort of stuff. And I think the results of that sort of speak for themselves. If you can recover from those kinds of packet loss levels, I think we've got. I think we're onto something as an industry group. Of course, as ubiquitous as we believe the internet is, there are lots of US-based television stations that are working in only SDI infrastructure, so they have routers, and all connections in and out are via SDI. So we need to deliver a sensible form of SDI into the internet. So we've discovered that if we use an adaptive H.264 compressor, you can actually create a transport stream and then allow the transport stream to adapt according to the conditions that it's seeing on the internet. So that allows the compressor to ramp up and ramp down according to the sorts of conditions that it's seeing. The net result is that the stream appears at the other end and is decoded back to baseband SDI to provide a sort of a end-to-end SDI over the internet approach. So within DVB TR 101 290, there are a whole bunch of sort of transport stream measurement guidelines that you can use. And one of them is an interesting one. It's the continuity count. It's a relatively simple counter that counts from 0 to 15 and then goes back to 0 and counts to 15 again. And by monitoring that counter, you actually get some feedback on what's actually going on the network. You can see if it's dropping, if the network is actually dropping packets just by monitoring this transport stream. The other side of that, of course, is that if you can monitor the count and you're still getting broken pictures, and the continuity count still maintains its 0 to 15 structure, chances are that you've got broken images going in on the front end. Because if the path is recording as a good, clean path, then the data must be broken on the input side. It's a fairly simple way of going back over that. So that helps us do that. And then I just want to talk a little bit about the standards that are in place and the sort of activities that are in place around this. There are a number of solutions available that perform in this arena. The solutions, however, are largely proprietary, and they offer different levels of performance just by virtue of what they are. So the issue then is one of interoperability, because you could end up with a system that has vendor A at one location and vendor B at another location. And unless they're interoperable, they're not going to work. So to that end, under the auspices of the VSF, there is a group called RIST, the Reliable Internet Stream Transport. I saw Rick Ackermans, he's the chair of the group, and Wes Simpson, they're both here. So I really value the work that they're doing to guide this steerage through the process of interoperability. We do plugfests, and at IBC there was a live demo of data being delivered from disparate vendors, different parts of the world, working nicely together on a booth at NAB, at IBC, I beg your pardon. And then there's the SRT stuff is technology developed by High Vision, and they have done quite an interesting task of making this data available as open source. It's on GitHub, so you can get it, you can use it. And that allows us to, the SRT Alliance is a large group of vendors and end users that utilize SRT, and they promote the use of SRT around these types of applications. So you can see there's a lot going on around this sort of technology, and I think it's only a matter of time until this becomes mainstream. There are plugfests to assist in testing. There are, and prove interoperability. And I think you could, if you'd like to be part of that group, have a chat with Rick or with Wes, and I'm sure they'd be very happy to have you on board. And that's the end of Dr. Marco's presentation, with 1 minute and 25 to go. Pleasure.
Here we go, questions.
I'm Mahmoud Al-Dakak, I'm CTO of High Vision. I appreciate you mentioning SRT and its implementation. Today we have 160 Alliance members. Some of them are extremely active. We welcome any collaboration with the RIST. Actually, we're active members also of RIST.
Yeah.
And our hope is just to make sure that everybody can interoperate, and having SRT come with RIST would be a very good thing to do. So thank you for mentioning it.
No, it's, my interest is in the connection of making it, I want to make it work too. Different people can implement different things, but at the very low level, you've got to be able to plug something in and it's got to work. Otherwise, the technology doesn't work at all. So that's my reasoning behind it. Lovely. Enjoy your lunch.
Thank you, Martin.
Of course. Thank you, Hans.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.